Marco Meineri from the Università degli Studi di Torino, and he's going to talk about the numerical bootstrap of points and lines. So the stage is yours. And
thank you very much. Okay, thank you very much, first of all, to the organizers for inviting me and for giving me the opportunity to speak. So I'm going to break the tradition or the use of the first few days of the conference. I'm going to give a mostly Blackboard talk. One of the reasons for that is that I've been raised in this cult, which was the Bootstrap collaboration, and there it's illegal to give slide talks, and so I don't know how to do that. On the other hand, since here it's much better, I can allow myself to show a few plots at the end by just unblanking the screen, so we'll have a few plots. And after all, this is my first time in Cambridge, but it's clear that we're at the center of the empire, and so things are good here. Okay, so today I'm gonna tell you of a method to do numerics with 2D conformal boundaries. So apply the numerical bootstrap to this problem and find some bounds on observables on CFT data. So the overview includes sort of a lengthy-ish introduction. I'm gonna be pedagogical because although most of the audience is made of experts, it's always nice to hear something you already know and be able to check your emails. And then I'm going to go on and discuss the actual technical part, which is a semi-definite program which can be explored numerically. And I'll give you a couple of examples with a few plots of the kind of bounds we can obtain. The caveat is that, so the stress is on the method. It took a while to make numeric works, as sometimes it happens with numerical bootstrap rather than on the examples per se. And one thing I'd like to actually get out of this workshop is some scolding for having missed the correct examples to treat and some suggestions on what actually would be interesting to explore numerically. And we're here for you, so please let us know what you'd like to learn. Okay, so I will start, as I was saying, with an introduction and with some propaganda. So there's no need here to convince people of importance of defects, but it's good to have I think, to reassure oneself of why we care. So I do want to do this. So the line of propaganda is, so why do we care about defects and boundaries? We care about them, and essentially because they pop up everywhere. And so even if you don't like them, you cannot essentially do without them. And there's people that have been trying to kill this field for a while, and they've never managed because, anyway, there's always a problem that involves a defect, and so these things come back. And why does this happen? Well, I think it happens because, essentially, defects encode the interactions at low energy between heavy and light degrees of freedom. So this is very general, and that's why defects appear everywhere. So if we have a theory with light degrees of freedom, gapless theory, then in the IR we'll have a CFT. But if there is some heavy degree of freedom of any sort, as long as it cannot decay, well, in the IR it will not be able to be kicked around by the light fields at low energies, and so it will become classical, and it will become a defect. So defects are just the only way in which the CFT knows about the fact that there was some heavy object in the theory before, and this heavy object, well, cannot decay for a variety of reasons. Typically, for instance, it has a charge, like this leads to Wilson lines in a medium which is either neutral or with charges that don't allow it to decay. It could also be stable because of potential barriers, like walls don't decay, although they're neutral, because you don't have enough energy to make the proton going to the electron. So there's actually a little bit more that one can say about this, although it's not the topic of this talk, but I would like to maybe give a shout out to a student who's working on this. So you can actually ask, can we describe this approach to defect CFT from a general fluctuating object in a conformal field theory? So this has nothing to do with the numerical bootstrap, but since I have a little bit of time, I will just mention it. So, if you have an object which fluctuates, well, at low energies, its degrees of freedom are given by its transverse fluctuations. This is something which will be familiar to the ones of you which know about the effective string theory. So you go to low energies, your theory was Lorentz invariant, because our word is Lorentz invariant, and so Lorentz invariance is spontaneously broken, and there are Goldstone bosons. And you might ask, well, okay, but then what are we doing when we describe defect CFT, where there are no Goldstone bosons, but there's like degrees of freedom, right? We don't have the Goldstone boson for the object that fluctuates, but we claim that we're encoding everything we need to know about low energy theory. So it better be that the Goldstone boson somehow decoupled in the infrared and leave us with a defect. And in fact, you can ask, what's the effective field theory that describes this process, in which in the IR I get something flat and rigid. And this effective field theory will have to have a defective point, which is our conformal field theory with the defect, and we'll have to have a deformation, which should be irrelevant, that restores Lorentz invariance. So by this guiding principle, you're kind of quickly led to write the following effective action, where this guy has been mentioned before, I think, in the conference. It will certainly be mentioned also by Philin later on, I think. And it's a displacement operator, so its role in life, well, for two-dimensional boundaries, that's just the boundary component of the stress tensor. Its role in life is to encode the response of the system to translations orthogonal to the defect. And so what happens when you vary the position of the defect? Well, the defect CFT action spits out, so the variation spits out precisely an integral of all the displacement times the transverse displacement. And the position of the brain, this x, transforms precisely by translating by the corresponding amount. Well, perhaps I should put a minus sign and the plus sign here, given the picture, but that's the same. And therefore, this action is invariant. So this coupling is dictated by restoring conformal invariance. And so that's precisely the way in which defects arise in our life from a continuum which is Lorentz invariant. And this coupling is irrelevant because the displacement has dimension equal to the dimension of the defect plus 1, so it's already relevant in itself, and you're adding a Goldstone boson. So this line of propaganda about defects arising in the IR can actually be made precise. There's an effective field theory there, and there's some further work to do in order to understand what the subleading terms are by asking that also Lorentz invariance, which is also spontaneously broken, is realized in the effective field theory. And okay, my student Tekla is working on this problem. She's also applying this here, so please hire her so that she can continue work on this problem. Okay, so this is the end of the line of propaganda, and now I would like to, now that you're all convinced, because before you weren't, that defects are important, I would like to move on to just the topic of the day, sorry, topic of the hour, which is conformal boundary conditions in 2 dimensions. And here, yeah, the introduction will be much more brief. It's just going to be to set notation, because there's too many members in the audience that know more about this than I do, and so I don't want to bore them too much. So conformal boundaries obey. So here I'm going to be in 2 dimensions, so I'm going to have a plane, which is actually the upper half plane, and the z real is where the boundary is, and then the boundary is conformal if Cardi-Bloom condition is satisfied. And if there are, if the theory has some extra symmetry, which could be any spin, but extra holomorphic operators, pair of holomorphic and holomorphic operator, you can or may or may not want to also preserve some of these. In particular, we'll be interested in the case of spin 1 currents later on. These both equations are valid for z, well, z equals z bar z real. So this omega is the choice you have. So what's the idea of these 2 equations? This equation tells you that there's no energy flow across the boundary, it doesn't leak, And this equation tells you that there's no charge flow across the boundary. But since there's this holomorphic factorization, well, you're free to choose which charge on the left you're going to glue to the one on the right, so you can rotate them a little bit, and so there's an automorphism there. So this one is not mandatory. Boundary conditions that only preserve these ones are conformal boundary conditions, and otherwise they might become rational if the theory is rational and you preserve the maximum number of allowed symmetries. So what's the status here? Well, if the maximal allowed symmetry is Virasoro, so if the maximal chiral algebra is Virasoro, then the fact that you preserve an entire copy on the boundary allows you to solve for the boundary conditions, because essentially you have a finite number of characters, so you might imagine, okay, there's a finite sum, I can solve. And if the chiral algebra is extended and you still preserve the maximal subalgebra, boundary conditions are also rational, if the theory was rational, and again you can solve. If you take already a rational theory, but you ask to preserve only Virasoro, or maybe a small enough subgroup of the chiral algebra so that the boundary theory is not rational anymore, it has infinitely many blocks, then essentially the game is over, or it becomes very hard. And there's some space which opens up for numerics, which is what we would like to tell you about today. Okay, another little bit of notation. Of course, in the case of when there is a boundary, there's boundary OP. So the boundary OP, well, we know how to derive its convergent. We just take a bulk operator, we draw a half sphere around it, and then we expand the state of the sphere in a sum of local operators. Oh, sorry, in a orthonormal basis, and then we use state operator correspondence. So in the end, we get a sum over boundary operators, which whose scaling dimension I'm going to denote with H, and the coefficient in the bulk boundary P I'm calling B. So in general, it depends on the bulk operator and on the boundary operator, and then okay, at of H, and there's some kinematics that I'm not going to report. And of course, I can also do the opposite, which means take the boundary, turn it into a circle, cut a sphere around it, and now the state in the Hilbert space, now it's a bulk. The state is in the bulk Hilbert space because I'm drawing a full sphere, and therefore the state, and for a boundary creates a state in the bulk Hilbert space of the theory, which is the boundary state, which I'm going to normalize. So let me just write the state here. Now this is a sum over bulk operators. These bulk operators have only spin 0. This guys, this AO, is the notation I'm using for the one-point function of each bulk operator. And G is a normalization which is required. It's a G function, and I will just review in a second because it's a piece of the equations that I'll need where it does appear and why did I need to put a normalization there. Okay, this sets up notation. And now, what are the constraints on the... Yes.
This O is a bulk operator?
Good, yes, O is a bulk operator. So the idea, so this is the boundary state. So this one's, I'm not being precise, I'm using any part of the chiral algebra to resum part of this OP. If I was to resum it here, I would write a Nishibashi state. And so this guy is a bulk operator. And at this level, the bulk operator is there just because I took my path integral where I insert a circular boundary. I cut the path integral outside, and then I remove the interior, and I write every correlation function in the presence of the state irradial quantization created by the interior. So since I'm drawing the full sphere, this state belongs to the bulk Hilbert space. Bulk, I mean, away from the boundary, there's no longer figure. The bulk Hilbert space, and so it has an expansion in a set, in an orthonormal set.
If you have a boundary interaction, how can deal with it?
Ah, that's a very interesting question. Yeah, so it is counterintuitive, and in higher dimension, there's been some discussion about how this plays out, etc. It is mandatory. So it's true that if you have well, in 1D there's not a lot of boundary criticality, but in general this mechanism works, and you might ask, well, okay, but I'm coupling on the boundary some extra quantum field theory. How comes that I can express this in terms of boundary state?
Even in the same CFT, you can have a boundary interaction. There are examples where you have boundary term just on the boundary.
Yeah, for instance, also here you can do this.
Yeah, but if you have only bulk operator,
Good. So the boundary interactions are encoded in this in the one-point functions fully. They cannot. So you see, there cannot be anything else. This is just a statement about the completeness of the Hilbert space in radial quantization. And if you have something that cannot be expressed in terms of bulk operators, the effect of that is that it's decoupled from the rest of the theory. It's the corresponding piece of the state. Imagine that this boundary creates a state which lives in a larger Hilbert space than the bulk theory where you are, than the CFT where you are. Well, it means that the piece of that state doesn't have an element of the, it's not expressible in terms of the local operators in the bulk, so it just has zero overlap with any state of the CFT. So anything that cannot couple this way, it's just decoupled by definition. And therefore, all the complications of the boundary are encoded in the boundary states, in the coefficients of the boundary state.
But Marco, your state is not normalizable, and I mean the boundary state is not in the Hilbert space.
Good, so the boundary, this is why I was careful to draw the sphere a little bit out. I didn't draw the sphere on top of the boundary, I drew it a little bit out. This state is fine, it's perfectly normalizable. Right? There's a little bit of time evolution, you do, like, you want to compute a normal state.
Euclidean time.
Of course, yeah. If you want to compute a normal of the state, this is actually it's a drawing that is going to be useful in a moment. The normal of the state is obtained by reflection with respect to this surface, right? So inversion, I should say. And then this is the normal of the state. It's the annulus partition function that's finite, particularly because Anatoly taught me that it's finite. So yeah, so you can write, so the fact, it's true that Ishibashi states are typically said to be non-normalizable, which is correct in the sense that if you really cut at the position of the boundary, then it's the same as taking the complete open string channel, like the diffusion here, and then you get the divergence. Any more questions? Okay, so then let's go on. I wanted precisely to come to this picture. Maybe I'll redraw it. Anyway, so what constrains the boundary states? So we see there are new pieces of CFT data, which we all know and love, one-point functions and the bulk-to-boundary two-point functions. We would like to know what constrains them, and this is a problem that was tackled by Cardi and Llewellyn, and the set of constraints is known since a long time. So these are the sawing relations for boundary CFT. And I'm not going to need all of them, although it would be nice to include all of them in the bootstrap. Perhaps the most important one, or the most famous one, is open-closed string duality, which precisely has to do with the annulus. So if I redraw it here, so since there was a couple of questions about this, maybe I'll just rederive it for fun. So I have two ways of writing the annulus partition function, and in terms of a sum over states. One way is to cut the Hilbert space as we said that way, and the other way is to cut the Hilbert space on a segment. And the reason is that we always want to write foliations of the Hilbert space which are conjugate to an isometry, otherwise it's very hard. And so we do that. And now on this side, it's pretty easy what's happening. So if I call this, this radius, I call it 1, and this one I call it e to the r. Then I start from somewhere here. I have a boundary state, which I can call B, which is precisely this guy. Well, it's this guy. Now, sorry, let me put quotation marks. I don't want to be too precise and waste a lot of time, but it's true that here I didn't put the time evolution. So actually, yeah, this is B, and here there should be quotation marks. Just this is probably why Kostas asked the question. So here I should have put some time evolution in order to be precisely to give precisely this picture. Yeah. So B, and then there's the time evolution that I was saying, e to the minus h times r, and then I close off again. So this is fine. This has a clear expression. In terms of a sum. Should probably go up because this will go back of bulk operators, and I get those one-point functions squared with their scaling dimension. And now what's happened on this side? Well, I have certainly a trace of e to the minus beta, where beta is this length, and then some other Hamiltonian, which is the one that rotates there. And the question is what this trace, what does it run over? And we do know, of course, what does it run over in 2D, but it's interesting to notice that this is the main obstacle in repeating what I'm going to do in higher dimensions, because this side, we don't know what it is in higher dimension. We don't have a good basis for this space. But in 2D we do. And how do you derive it? Well, you have the Hilbert space on a segment. So we just write it as we usually do. We continue Euclidean evolution, and we put something at the bottom. So if I write a bracket, I continue also to the top. And then I can do a conformal transformation that maps this precisely to the before, which is why I drew it. And it tells me that the states on the Hilbert space on the segment are in one-to-one correspondence with states in radial quantization around the point, which are local operators on the boundary. And so I get the second, I know what this trace runs over, it runs over boundary operators. So I get the second side of the equality with some integer, e to the minus beta, times their scaling dimension, which I call in h. Okay, so this is open closed ring duality, or the Andrews partition function. And what's important for us is that this is positive for a unitary theory, it's an integer, and this is positive for a unitary theory. Okay, there's other Sohn relations, and in particular, I'm going to need two of them. One is the two-point function of an arbitrary pair of identical bulk operators. And here, crossing, so the two different expressions, is given by either fusing these operators in the bulk or fusing them with the boundary. So on this side, I'm taking first the bulk of B, which I didn't write there, but it's of course present in any CFT, so you just fuse them and you get sum over operators in the middle, and these operators do have a one-point function. I drew it there, I wrote it there as proportional to A, and so we get some sum over bulk operators, delta. And then this three-point coefficient, phi, let's say O delta, and then the one-point function corresponding with some, again, some function, which some kinematics that, let me just say that it's a function of a cross ratio that I'm calling psi. And then on the other side, instead I do first a boundary fusion, so I get the sum over boundary operators, and then I get twice the square of the boundary P coefficient that I had there, times some other function. Okay, and here the data aside of the scaling dimensions that appear are these ones, and this one is crucially not positive, not necessarily positive. It can be made real, but it's not a square, so it's not necessarily positive in unitary theory. And the last relation doesn't involve the boundary at all, it's just the four-point function of the same identical operators. Which, okay, this is a favorite equation for many people in the audience and many of my friends and myself, because it provided quite a few of us with some fun and some tenure track position at the end, so we all liked it very much. And okay, here what this looks like, it's the sum. It's the sum over the square of the P coefficient. I have them twice. C phi O delta squared times some function of two cross ratios equals 0. I brought everything to the left-hand side because in any case they run over the same sum. Okay, so there's other Sohn constraints. The bits that is known, as I was saying, but I won't need them. Okay, so what's the status here? In order to for the numerical bootstrap. So this constraint was. So is this what I want to say now? I think so, because I want to move on to point 2. There's still one bit that I want to say about the data before actually moving on to the numerical bootstrap, so let me say it. I mentioned before that I was normalizing this state with an extra g, and since this is one of the targets then of the numerics, I want to just remind you of why. The y is that this trace, for this being integer, this means that the boundary state is normalized. I cannot just rescale it by a constant, otherwise those are not integers. So in 2 dimensions, there's a fixed normalization for the boundary state, and since I had chosen the one-point functions to be proportional with some known kinematics to this AO, then I have to allow myself for a specific normalization. And this value of G, which then is physical, it's the overlap. So G is the overlap of the vacuum bulk state with the boundary state. And it is rightfully famous, not just because it is physical, but because it has few nice properties, most important of which, well, what do I want to use? This point is fine. But it's monotonic under RG, boundary RG. So we had a talk yesterday about the same property for a quantity in ADS by Lorenzo, and this was proven by Freedom and correct me, Anatoly, who is in the audience, in 04. And okay, earlier on, Affleck and Ludwig noticed that it appears in entropic quantities, which you should expect for a monotonic quantity, probably, and in S of T and S entanglement entropy. So it appears both in the finite temperature partition function on with the segment, and in the entanglement entropy for a segment that for an entangling surface for an entangling region that crosses the boundary. Okay, so now let's move on to part 2 of the talk, if there's no other questions. So I will raise down there.
You're not going to include the bulk modules in your set of conditions.
Right, the torus is not included now. Yeah, so
But the 4-point function is.
the 4-point function is, and the reason why the 4-point function is and the torus isn't is what I'm going to explain now.
Excuse me.
Yeah.
The sum you wrote there, the bottom, yes, the sum there, the sum of the primal, which kind of all the Virasoro.
Okay, thank you for the question. Yeah, so it's the sum of all scaling operators, and then what you organize it by changes these functions f and g. And the largest chunk of your Hilbert space that you can resum is constrained by the largest chiral algebra, which is preserved by the boundary. So in particular, this maybe gives me a way to already point you towards this board, which you don't have to look at in detail, but it's just useful for when there's questions. So that sum there is written in a slightly less excruciating, like a slightly more readable form here. Oh, I don't know if it's more readable, it's more precise. And here you see I specialize these functions, and they're expressed in terms of the cross relation. There's some function kappa here and kappa there, and these are the same functions actually with different variables. What is kappa depends on what part of the chiral algebra you're resumming. So for instance, if you resum only, let's say, quasi-primaries, which is something that I will do when I do numerics for simplicity here, then this kappa is a 2f1. If you resum all the Virasoro primaries, then this kappa is some infinite sum of 2f1, is a Virasoro block, and it's actually the same Virasoro block, it's the same function that appears in the 4-point function. So this is a consequence of, well, you can see it in various ways, but the simplest one is probably the method of images, that these functions are actually the same. So these are just conformal blocks. They're the same set of functions that appear in the 4-point function. And if you were to resum also, say, you have a full chiral algebra which is preserved, then you have different blocks, and these are the chiral algebra blocks.
Okay, but on the right-hand side, the left-hand side is not the same sum in general.
These are not the same sums, and so it may be a bit surprising.
You have one continuous, one discrete.
Oh, I'm going to assume that scaling dimensions are, well, actually, I'm not assuming it when I do numerics. Like in writing, I write sums because it's best, but the numerics doesn't really care if the sums are continuous. As soon as they're, I make specific assumptions, like the fact that there's a gap and some isolated operators may be at the bottom, and then both of them could be continuous. But they're two different sums, but it's important that although, well, it's important for practical purposes that although the two are different sums, the functions are actually the same function. And And yeah, I can explain this. It's simply related to method of images, but in general, the source of this is that the Virasoro algebra is just one Virasoro algebra. So the way it acts on operators on the boundary and in the bulk is very similar. Okay. So let me erase.
So include bulk crossing but not modular invariance because this consistent equation is more local and the modular invariance.
Yeah, give me just a second. I explain precisely why I'm including one and the other. Okay, so there's already a history about doing numerical bootstrap with two-dimensional boundaries, and in particular, this history is regards this crossing equation, which is written in a more complete form. Is the first equation there, where chi are just the characters of the corresponding Carrel algebra. And this history starts quite in the early days of the conformal bootstrap by a paper by, again, Friedan. Connect me in the audience, and Schmidt Collinet in 2012, which was really the early days of the conformal bootstrap, so that was quite pioneeristic. And then, much more recently, Scott Collier, Vladimir Mazach, and Ifan Wang, in 2021, they use sort of the modern machinery to derive a wealth of very nice results about essentially the G function of boundary conditions, so the G value, the G number here, bounding them by inputting the central charge and some assumptions about the spectrum, for instance, stable boundary conditions. And okay, so why can one do this for the annulus rather straightforwardly? Because these two quantities are positive. And therefore, this is a convex problem. So the conformal bootstrap is an exercise in convex optimization. If you have a convex space, convex spaces are easy to optimize, because if you want to know what box bounds your convex space, what you have to do is to run like a maniac until you hit a wall. And once you hit a wall, you just ask what the derivative is. Like if you can go further in one direction, you keep going until you stop. And that's it. Instead, if the problem is not convex, that's not the end of the work. That's not the end of the game, because it could just be in a local extremum. And so, why is this a convex problem? Well, if the two are positive, so this equation, let's say I have two solutions of these equations, then I can sum them up and obtain another solution. So, fine, so I can take linear combinations of solutions, but now, since the two coefficients need to be positive, I have a chance of getting a bound, because I cannot take arbitrary linear combinations. They need to be positive linear combinations. So, and then further, so maybe I can write this. So I have some set of, let's say, just for one coefficient, but it's a vector equation. Actually, let's write this vector equation. Alpha plus beta A1, A2 still gives me a set of OP data, say this in dimensions, but I should do it also for the n's. Which is the solution. And then, why is there a bound? Well, alpha and beta are positive, but also I have a normalization. I can just pick boundary conditions which are elementary, which means that there is only one identity, so n of 0 is equal to 1. And then to preserve this condition, I need alpha plus beta equal 1, and then alpha greater than 0, and beta, and so therefore less than 1. And so then I precisely have a convex space, right? I can include every segment between two solutions in the space of CFT data and not more. So now what happens if I have something that is not necessarily positive? This reasoning is out of the window, so linear combinations are fine, but they don't have to be positive. They need to be normalized, so this condition is still valid, but then alpha is not bounded. So this equation was a bootstrap favorite of the, in particular the higher dimensional bootstrap, not only, for boundaries and defects. This seminal paper by Leonardo Rastelli about Varese and wait, where am I? So, sorry, yeah. I just want to find the. Okay, so the third name is better at the end. Of course, I stopped mid-sentence because I wanted to find where I am in my notes, not because I did not remember the name. Here, okay. Yeah, so Rastelli, Van Ries, and Liendo in 2012, again, they did they played this game with this equation, and they assumed that this product was positive. And a few of us did the same later on. And otherwise, you can find something else. For instance, you can discretize the sum and truncate it and hope for the best. Okay, so what we would like to do now is to include this constraint, because this is the first constraint that includes information about the b's, so the path-to-boundary B coefficients. We would like to make a step forward and so include it, but in a way which is compatible with rigorous conformal bootstrap. And so that's why we include, so this should answer the questions that were asked, why we include the 4-point function. We include the 4-point function because the 4-point function has this 3-point coefficient squared. The 1-point coefficient appears squared already here, and so we're fine. So why is this fine? Because if now I take really the sum of this equation plus this equation plus that equation, so the 3 equations that are up there, then in the resulting equation I have at least everywhere, at least somewhere, sorry, in some term, each of the coefficients appears squared. And then you can, first of all, it's intuitive that then the problem is bounded, right? I cannot run off to infinity, there's some potential. If I take a coefficient very, very large, it contributes squared with a large positive number to some term of the equation, so the equation cannot be satisfied. And then second, more technically, you can just repeat this reasoning, but in the space of the square root of B coefficients, and you'll find that it's actually a convex problem there. And so that's why this set of equations is the minimal set of equations, which allows me to find bounds on rigorous bounds from the 2-point function of bulk operators in the presence of a boundary. So this is called, I'll just write it here. Just for references, the paper, since I'm writing some of the more important references, Rastelli. Well, Liendo, sorry, Liendo comes first thing before calculate order. Liendo, Rastelli, Van Ries, 2012 as well. And then the correct reference here is for semi-definite programs is David Koss, Poland, and David Simon Staffin. In 2014, who taught us this technology of putting together various crossing equations to get something positive. Okay, so I'd just spend 3 more minutes with some information about the knobs we have, and then we'll move to the examples, and I'll show you some plots of what you can obtain by applying convex optimization methods to this problem.
Sorry, just to understand.
Yes.
So the equation you are putting together is the first one, then this one, yes. This one and this one. Okay.
So those are up there, and those are the equations that I put in the convex optimization. Yeah, I can give more detail about how you actually implement, how you turn this into a problem that can be put into a computer. I'm just not going to do it for reasons of time and interest, but if you're interested, I'm happy to. There's some slight variation with respect to the standard conformal bootstrap, because as you see there, you have different cross ratios appearing. And so, well, typically when you do this with a bunch of 4-point functions, you have the same cross ratio, so you just pick a point and you take derivatives around that point. Here you need to be a little more careful about how you pick the point in order to use what's called, to turn into what's called a polynomial matrix program, but it's not, it's a technical point, so I don't want to spend too much time on it. Okay, so the last bit of information before going into some plots is the parameter space. So there's various knobs in these equations, and so how does the bootstrap work? The bootstrap tells, well, there's many iterations of the bootstrap, but the simplest version is I give you, or you give me a trial spectrum, and I tell you if that's an allowed spectrum or not, if these equations can have a solution or not. And so rather than giving a detailed spectrum with all the operators up to infinity, which would be a bit be a rigorous result, but maybe not super interesting in most cases, one can ask something about the low-lying spectrum. So in particular, about gaps. So can I have a theory in which, can I fix a theory and ask if there is a boundary condition with no operators with scaling dimension below 10? So that's a question I can ask. Is it compatible with the crossing equation? And I expect that probably the answer is no. Well, of course, we know the answer is no if I don't put any extra, if I don't say anything extra, because the stress tensor has a boundary limit, but let's say outside of the identity module. Okay, so that's why we will give gaps as parameters to the bootstrap. So first of all, there's one number which is not a gap. I need to pick an external operator, so that's the scaling dimension of the external operator in the plots is called delta phi, so scaling dimension of external operator, so the one whose correlation function I'm computing, and it appears in various places in the crossing equations, in particular in the second equation it appears explicitly. And then there's gaps. So delta gap is going to denote the lightest scaling dimension of the lightest operator whose one-point function doesn't vanish. So what do I have to say? Yeah, lightest operator in phi, so belonging to the p phi dot phi, such that O is different from 0. Okay, so if it's 0, it doesn't appear in this equation, and otherwise it appears. So that's my gap to the continuum spectrum. You can do something more sophisticated, which you do from time to time. So we put some isolated operators and then a gap above it, and then delta gap will indicate the gap above it. But that's the idea you should have in mind. So this is about the lightest bulk operator. Then there's something about the gap telling you something about the lightest boundary operator. So the lightest O hat on a certain boundary condition. And then we have a separate gap which we can access in this mixed system, which is the gap in the two-point function. So this is the lightest boundary operator in the boundary OPE of phi. And so there might be a selection rule. Let's say the boundary preserves some symmetry and phi is charged, and then the lightest operator in the boundary OPE of phi might not be the lightest operator in the theory. So technically, this is a knob that allows us to find boundary conditions that have some selection rules. There are some gap above the lightest operator in some correlation functions, and it also allows us to use the power of the second equation a bit more, because the sum on the right hand side really runs only over operators that appear in the boundary P. So we can dial it to make that equation to be the more constraining one. The fewer operators are in an equation, the more constraining the equation is. Okay, so that I think concludes, and I can for.
I can think examples where there just aren't any in each of these cases.
No operators.
Yeah, very simple cases.
Okay, please. What?
Well, like
I'm confused.
With the elementary boundary conditions, or take bulk fields which don't couple to anything except the density on the boundary.
So you're saying I can have example where these guys are only, yeah, I see where the question is coming from. Thank you very much for the question. So I didn't tell you what kind of algebra so I didn't tell you primaries here according to any special kind of algebra. So for instance, it could be that H gap is infinity in the sense if I have I don't know, minimal model, I'm looking at a boundary condition which only has the identity, and then if I tell you, well, the gap above the identity Virasoro module could be infinite.
Yep.
Yeah. So when we bootstrap, I'm going to show you plots of two different kinds. One kind is the Sawyer relations, so only one equation, which is the one that is positive on its own. It's the one that was already analyzed by these three people in different cases than what I'm going to show. There is some Virasoro, and so that's the gaps that I'm going to discuss. But I'll be discussing C=1 and C=3/2, so not this case of the minimal model where you can only have the vacuum. And then instead, when we bootstrap the whole three equations, because the bootstrap for 2D CFT Virasoro, it's a bit in its infancy still. For this round, we just use SL2C. So I'm going to actually sum only SL2C, and these are quasi-primaries, and then, thank you. Okay, let me turn on this thing. I should get rid of the backwards. It's already on. But I don't think I did something. There's something magic. Okay. Good. Okay, so the most important thing in this slide is this logo. This logo has to appear in everything I do, otherwise they don't reimburse me. So please, if somebody asks if you've seen it, you've seen it. And now I'm going to treat two very simple cases. This one is just a free boson, and the other one is C=3/2 with emphasis on the simplest non-trivial WW model, so K=2. This is a slide which sort of summarizes free boson boundary conditions. I'm not going to go in much detail, also because what we're going to focus on is really, the idea is to test the method in a case where there is a modulus and where there is a fairly good understanding, or conjecturally at least complete understanding of the boundary conditions. And so I'm going to focus mostly on boundary conditions for the circle branch. So just as a reminder, the compact free boson is a theory with C=1, with a shift symmetry, U1 shift symmetry. There is a radius which is dimensionless, and so it's a modulus. And there is T-duality, which is a duality that exchanges large radius and small radius and reorganizes the operator. So I'm going to focus on R greater than square root of 2 as a frame. Since we're in 2D, the U1 symmetry has to be to double up, so there's two U1s whose quantum numbers are reflected in the scaling operators of the theory as M and W, momentum and winding, and those are their scaling dimensions and spins. Boundary conditions for the circle branch, so for this theory, fall in two classes that are Dirichlet and normal boundary conditions at generic radius. I'm talking about boundary conditions with a normalizable vacuum, just for the precision. That's why the asterisk. And okay, they're exchanged by T-duality. There's a circle of each of these boundary conditions. All their data is known. G function, boundary gaps, one-point functions, etc. The Dirichlet branes break one of the two U1s, and the Neumann branes break the other. These two are exchanged by T-duality, which is just the exchanging of D bar phi with minus D bar phi. There's other boundary states for the Z2R default, where the U1 symmetry is already broken in the bulk. And there's some more exceptional branes, special radii, and some people in the audience, including Gerhard, are responsible for analyzing them. So here is the first plot. So this is a plot of the annulus, so it's only this equation there. And therefore, it's a plot that contains both a bound under Virasoro and a bound under the assumption of just SL2 symmetry. We plotted the gap in the, so the lightest bulk operator, which gets a one-point function against the lightest boundary operator. And so this is kind of nice organizing principle for boundary conditions in the free boson. You find many of them. I don't have time to go in detail, but these are all essentially the boundary conditions that are known. So what are the generic features of these plots? These are generic features of every bootstrap plot. So when you increase the gap in one channel, so you put fewer and fewer operators, well, something else needs to yield, so the gap in the other channel goes down. So this kind of feature is always present. And then this green line is the SL2 bound. It's kind of boring. And this one, which is the one under which the allowed region is Virasoro bound. The non-boundary conditions are denoted with some like this blue line, the red dotted lines, etc. So blue is just the circle branch boundary conditions, Dirichlet and Neumann. Actually, probably I have some. Yeah. So you see that it kind of the numerics kind of wants to match the known classification of boundary conditions. So these are sort of all the boundary conditions that there are. There's some isolated points corresponding to the boundary condition I didn't explain, which appeared. I should have put Yannick here as well. I don't know why I forgot it. I'm really sorry about Yannick. So there's a bunch of papers from 2001, 2002 where these were discussed and conjecturally classified. So this is a circle branch, the blue ones. And just as because I'll need it in the following, it's important that the circle branch boundary conditions can never have a boundary gap above 1, because I'm considering Virasoro, and these ones preserve at least one U1. So every time you have a current, so an holomorphic operators have non-singular fusion with a boundary, always, and therefore give you a boundary operator which has a dimension of the bulk current, so in particular, in this case, 1. So there's nothing about this. And what this tells you, well, it tells you, for instance, that if you want to have gaps on the boundary channel which are larger than 1, you need to break the U1. And so in particular, for instance, this is a fractional brane in an orbifold, and there's a larger, it's a set of fractional branes, and there's a larger gap. This region which is colored, it's because if you go to the Z2 orbifold, you broke the U1, and then you don't only have the radius of the bulk as a modulus, but also the position of the brane that appears in CFT data, and therefore you have a two-dimensional region. Okay, this I already said. And there are some changes in slopes here, which are associated to the general representation of the Virasoro algebra. When I increase the gap past one of these degenerate representations, I have a jump in the structure of this equation, and the bound reflects that. So now we would like to focus on two boundary conditions, Neumann and Dirichlet, and say a little bit more with the full system, essentially what I've been advocated as the main point of this talk. So here, I'm first focusing on Dirichlet, and then I need to put assumptions that tell me that there's Dirichlet. And so actually these assumptions are best discussed here still for a second, which is, so I would like to have, with Dirichlet boundary conditions, a one-point function for something which is charged under the momentum symmetry, because D branes break it. And in my duality frame, the lightest operator, so the only operator, the lightest operator is a momentum mode, and it has dimension less than 1/2. So therefore, if I want to have a one-point function for this guy, well, I'm sitting here. So this is the Dirichlet boundary condition place, or at least they cannot, they must lie here, and therefore H gap I can set to 1. So that's how we get this assumption. And then to get better assumptions for the other equation, so this equation there, I'm going to assume sort of a sparseness condition for the boundary OP. I'm going to say, well, I'm not going to put any operators which is not needed in the boundary condition among the charged operators. So this is sort of typical of symmetry breaking boundary conditions. They're rigid, and so the boundary spectrum is sparse. You have only the operators that are really necessary, and therefore this gap in the two-point function, so I'm considering as a bulk operator the momentum mode, so it couples to the neutral sector, and the gap in this two-point function is going to be reflecting that. So this 2 comes out because I'm setting the gap above two operators I know need to exist. One is the so-called tilt operator, which is just the boundary value of the current. The second one is the stress tensor, and then I'm going to be agnostic about what's above that. Okay, so what am I plotting? I'm plotting the one-point function of the bulk field, A phi, against essentially the radius. Delta phi is a proxy for the radius of the free boson. And here what I want to notice is that these lines, red lines and blue lines, are the SL2 bounds for the annulus only. And instead, the green region is obtained by the full system. So this, the extra 2 equations give a lot, give an order 1 improvement in a large region of the parameter space over the single equation. Of course, we know the exact result, which is 2. But it's good to see that this mixed bootstrap of local operators, points, and lines can improve. It doesn't always improve, so this is a plot for the Neumann branes instead. And here I just want to show one feature that happens sometimes in this kind of problems. So here we're plotting the bounds on the G function. So G function cannot be larger than this value and smaller than this value with the assumptions we're using at two different points in the moduli space. And two different things happen. So here, this is the non-membrane, this point here, and here is the non-membrane, this point there. So in this case, the non-membrane lies in a place where if I change the gap on the boundary channel, well, actually this should be H2-point gap, I'm sorry. If I change the gap in the 2-point function, nothing happens. So I can change and the bounds are unchanged. What does it mean? It means that the bounds are fully fixed by the annulus. So in this region, when this happens, so in this region here, the additional two equations are doing nothing. They're just completely decoupled. The optimal solution is just a solution that sets them to 0. And in this case, instead, the actual boundary condition we know that lies in this space is in a region where this bound is curved, and this means that the 2-point function gap is doing something. So if I make the boundary condition sparser in this channel, so this equation is harder to satisfy, this influences the g function that appears in the first one. And so this is the situation. So if you want to see what happens, so the first situation where nothing is improving is this region of the modular space. And here you cannot see the bounds because they are superimposed, but annulus bound and mixed system bound coincide. And in this region instead, which is the inset here, this is the annulus bound, and this is the mixed correlator bound, and the non-membrane appears to be extremal. So in the last minute, yeah, I got a bit delayed with these plots. So there's I'm going to skip introduction about the SU2 WSW model. Everybody knows that anyway. And I just want to show you maybe one last plot. So you can repeat these things that we did for C=1 for C=3½ and you find sort of similar results about boundary conditions in a theory which this time is not known, whose set of boundary conditions is not even conjecturally known. So these are bounds which are bounding things that hopefully are not fully known. And in particular, I'll focus on this plot. Just it's not the most interesting plot, but it's one plot about the full system. So here we're plotting this gap. So the SU2 level 2 WSW model is a theory which doesn't have moduli. So what we're varying here are just boundary gaps. Because the bulk is completely fixed. We're assuming it's known. We're actually inputting it. In the best bound, we're inputting scaling dimension of bulk operators and some of their OP coefficients as well. So we're trying to focus on one theory and ask what boundary conditions can it have. And here we're plotting the gap of the boundary condition against the lightest operator that couples to the bulk operator whose correlation function we're computing. And so this line, its plot is not at 45, it's not the same scale, but it should be 45-degree line. And it's just a statement that you cannot have an operator in the 2-point function which is lighter than the lightest operator in the theory. And the upper bound, instead, it's the maximum selection rule that you can have in a boundary condition in SU2 level 2. So there cannot be a boundary condition which has, let's say, 0.4 as the lightest operator on the boundary, but somewhat more than 1.5 as the lightest operator that couples to the bulk spin-a-half operator. And so the fact that this line doesn't go to infinity, it's a rigorous consequence of this 2-point function. So this is kind of this rigorous bounds coming from 2-point function of bulk operators in the presence of a boundary. And the two blue points are the 2 points that you obtained by plotting in these variables the known boundary conditions for SU2 level 2. And the hope is that maybe there's some new ones that lie here, and with better assumptions or more numerics, one could narrow this region down a bit. Okay, so let me conclude. I just want to essentially repeat something that I said at the beginning. So here we just discussed two very simple examples, one for which there is a conjectural classification, and another one for which there's only a few known boundary conditions, and hopefully there are more. It would be nice, and it certainly will be nice, to treat more examples. And also we've done conformal bootstrap without sort of the best machinery that one can use. There's many knobs to play with, and there's technical improvements which are available. OP scans in particular, we didn't use Virasoro symmetry, etc. Clear improvements would be to use all the Soin relations or to use correlators involving boundary operators as well, which is something that in a different setup is already underway. There's work on similar topics, both by Max McLeese and collaborators and by Miguel Paulus and collaborators. And it would be nice to also look at higher dimensions. And for the last plot, by thanking you, I'm going to show you the most fun place I've been this year. Thank you.
Thank you very much, Marco, for your wonderful talk. Are there any questions?
Yeah. I'm just wondering if having 3 equations helps relaxing conditions on the bulk gap to get a lower bound on the boundary entropy.
Yeah. So so the question refers to the fact that if you just use the annulus, one thing that was noticed by Anatoly and collaborators is that if the central charge, if the gap is not large enough, so you have operators which are too light with respect to the central charge, the identity block, the identity character, is crossing symmetric on its own. And therefore you cannot get any bound on the G function because the normalization that I was telling you about, this 1 for the boundary identity, can be changed at will just by adding something proportional to the character itself. And I don't know, because we didn't use Virasoro in this case, but that is my hope as well. So there's no specific reason why. So this is a question about the crossing kernel, so it's a question that is finite complexity. Perhaps I should know the answer, but since we focus on SL2, we didn't look at it. But there's no a priori way why this should be the same story also for the two-point function, and therefore I hope that that this can improve a bit.
The case of C equal 1 and the exotic boundaries, there you expect the data to jump very much around as you move R, right? I mean, you only find things at rational R's and...
So there were a few of these points. A few of these points were shown in the plot. This depends. So we showed the points that lied in the region where we were looking. For instance, in this plot here. These guys are of this kind, and there's more forward, etc. So they typically have a small bulk gap, but they do their points which are in this scattered around in these points. They all lie in the allowed region, so we didn't find them to be extremal, but they are. Actually, some of them, the ones that live at C equal 1, the ones that live at H equal 1, are extremal, I think. So they're families of points that become extremal for the G function bound. This is a plot that was in the paper by Scott, Dalimin, and Ifan. And so that would be a slice of this plot where you put you sit at H equal 1 and you put G function instead in the axis. And there you separate some of these boundary conditions which have the same gap, but they have different G function, and they found that we're approximating the lower bound of the numerics.
Maybe one last question.
So if I understand correctly, when you do the annulus, you have the same boundary condition on the two boundaries, right?
Correct, yes.
Can you put different boundary conditions?
Very good, thank you. Yes, you can. So again, in that case, you would need to enlarge your system, because if you have two different boundary conditions, then the coefficients in the bulk channel are not anymore positive, because you have the product of one-point functions. And so therefore you need to add to the system also the annulus with identical boundary condition equal A and identical boundary condition equal B.
So you have 5. I mean, how many?
Yeah. You at the point you would get 5 equations. But these things, I mean, you're part of the inventors of the topic, and people after you have gone a long way in your footsteps. I mean, it's people can treat a lot of equations. These are not big systems.
Do you expect to get more information in this strange case?
Yeah, because this case, if you do add the two different boundary conditions, then you have access to boundary changing operators, which are new scaling dimensions, which here I don't see. Here, the only operators that I see are the ones that are supported on a single boundary condition. That your quantization, the sphere touches the same boundary condition on the left and on the right. And instead, if I consider the annulus with two different boundary conditions, then the set of the Hilbert space there is a space of boundary condition changing operators, which is it's not accessible here. It's accessible, actually, I should say, just to reply convincingly, so it's accessible in an indirect way, because I'm not always imposing, I cannot always impose that the boundary condition is elementary. I'm normalizing the identity to be 1, but I could take any boundary state and normalize the identity to be 1. So in the support of some of these plots, there were, like in some plots, there were some lines that I didn't have time to insist on, and these lines were corresponding to non-elementary boundary conditions that we know are inside these plots. But I cannot use these as knobs. I can never set a gap which only, for instance, gaps the boundary changing operators, which instead I would be able to do with your suggestion.
Okay, I think we'll leave other further questions to the coffee break, so let's thank Marco again. Thank you.